Hello everyone, welcome back. Today we are going to do some practice problems involving rotational physics and, more importantly, moment of inertia. On that note, if you are not familiar with moment of inertia, please make sure you watch my previous video before this one, otherwise this video may get a little confusing. And speaking of moment of inertia, the first thing we're going to do is add to our linear rotational chart here. First, we actually have one core variable to add, which is going to be kind of like these first three. And that variable is mass. SI unit, kilograms. Rotational unit, moment of inertia. Again, please be sure to watch my moment of inertia video if you're not familiar with this. Units are kilograms meters squared. Next up is an extremely important one, the most powerful equation in macrophysics, Newton's second law, which is acceleration is F net over mass. Rotational version, angular acceleration is net torque over moment of inertia. All right, so if you've been following, you should have this chart written down, and we could add our new ones to it. And again, we have our linear to rotational equations in the corner, just in case. A quick note before we start these. What I suggest is after we start the question, you take a good look at it, pause the video, try the problem yourself on a sheet of paper, and then hit play. That way you can test your own abilities and then see how well you did. Okay, let's get started. Problem number one. A 35 kilogram cylindrical satellite at rest has 4 small thrusters attached to it as shown. Speaking of as shown, here is the satellite. This is a side view over here, and this is a top or end view of the satellite. So it's basically the shape of a soup can. It is 6 meters long and has a radius of 1.8 meters. If each thruster can produce 2.5 newtons of force, and there are 4 of them, how long will it take for the satellite to reach an angular speed of 6 rotations per second? Assume the distance from the edge of the satellite to the center of the thruster is negligible. So what that last statement means is that you have a small distance between the edge of the radius here and the center of the thruster, and this problem is basically telling you just to ignore that small distance. Okay, let's start how we always start, which is by listing givens. First, mass is 35 kilograms. It's 6 meters long. Length is 6 meters. Radius is 1.8 meters. The thrusters produce a force of 2.5 newtons each. And while I'm here, that thruster is definitely perpendicular to the radius, which means we are definitely going to have a torque. So under this force perpendicular, there are 4 thrusters. The satellite's at rest, so omega initial 0 radians a second, and we are looking for a final angular velocity of 6 rotations a second. All right, the first thing I'm going to do is we don't want rotations per second. We want radians a second. 1 rotation is 2 pi radians, which is 12 pi radians per second, or 37.7 radians per second. And we are looking for time. Since I have omega initial, omega final, this is practically telling me I'm looking for angular acceleration here. All right, now that we have our givens, let's start seeing what we can find with these givens. For starters, something I immediately see is a radius and a force perpendicular, which means I can get the torque. Torque is force perpendicular times radius, 2.5 newtons times 1.8 meters, gives me 4.5 newton meters. And while we're here, there are 4 thrusters. So our total torque is 18 newton meters. And just a note, I'm kind of ignoring direction here, considering that it starts at rest. And I'm just implying that whatever direction this thing starts rotating in is going to be the positive direction, which according to my picture happens to be accurate. So a case in point right now, I know I'm looking for acceleration, and I just got net torque, which means at this point I definitely need the moment of inertia. This is in the shape of a cylinder. The moment of inertia of a cylinder is 1/2 mr squared, 1/2 35 kilograms, 1.8 meters squared, 5670 kg meters squared. This now allows me to get angular acceleration, torque net over moment inertia, 18 newton meters, or 5670 kg meters squared. I see 1 meter cancel right now. Newtons is kilograms times meters per second squared, which means both kilograms cancel, and the other meters cancel. So I now have 1 over second squared, or more accurately, 3.175 times 10 to the negative third radians per second squared. Again, radians pops up because radians is a fake unit. It does not exist. To finish this off, we're going to use our other angular acceleration equation, which is angular acceleration is change in angular velocity over time. We do not have initial angular velocity. So if I rearrange this, I get time is final angular velocity over angular acceleration, which is 37.7 radians per second, over 3.175 times 10 to the negative third radians per second squared. This unit is a fraction in the denominator, so it is going to flip, which means radians is going to cancel, and one of these seconds is going to cancel, and this last second is going to end up on top. That will give me 11,874 seconds. If I divide by 60, that's 197.9 minutes. And if I divide by 60 again, that's about 3.30 hours. And once the satellite gets to this angular velocity, all it has to do is shut off the thrusters, and it will continue at this angular velocity, because there is no friction in space to slow it down. And one more note, just for anyone who happened to notice, we had a given here that we did not use. We did not need the length of the cylinder. Sometimes you'll be given more information than you need just to see if it throws you off. All right, let's start problem number 2. And problem number 2 is going to involve this disco ball. The disco ball is obviously in the shape of a sphere, so that is definitely going to come into play. And we are going to assume it has a uniform density inside, which means it is not hollow. Here's our problem. A disco ball at rest is accelerated to an angular speed of 0.84 radians per second in 3 seconds. If the radius of the ball is 0.6 meters and the stand provides 0.129 newton meters of torque, what is the mass of the disco ball? So I put this one up here because getting the mass is kind of rare. Typically, you were given the mass to get the moment of inertia. But in this case, since you're hunting for the mass, it's kind of like the last problem we did, but in reverse. However, our technique is not and will not ever change. Number 1, list givens. First, at rest, omega initial is 0 radians per second. Omega final is 0.84 radians per second, which is pretty slow, which makes sense because disco balls typically revolve fairly slowly. We are given a time of 3 seconds. We are given a radius of 0.6 meters, and we are flat out handed the torque, 0.129 newton meters. So the next thing would be, what can I find with this information? And step 2 would be, list the equation I'm going to use. Right here, this is screaming to find acceleration. And if you can ever find acceleration or angular acceleration, you will always get it. Angular acceleration is omega final minus omega initial over time. Omega initial is 0, 0.84 radians a second over 3 seconds. Gives me 0.28 radians per second squared. I'm going to add that to our givens list. Now that I have torque and angular acceleration, this is screaming at me to get moment of inertia. Since angular acceleration is net torque over moment inertia is torque net over angular acceleration, 0.129 newton meters over 0.28 radians per second squared. Breakdown in newtons is kilograms times meters per second squared. This is a fraction of the denominator, so it's going to flip. That means second squared is going to cancel. Radians is a fake unit, does not exist. Therefore, I get 0.461 kilograms meters squared. So I have meters here and here, which is the proper unit for moment of inertia, so I'm good. We'll put that in my list. The last step is, since a disco ball is a sphere, the moment of inertia equation for a sphere is 2/5 mr squared. Therefore, to get mass alone, I'm going to multiply by 5, which is 5 times moment of inertia, divide by the 2, divide by the r squared, and that gives you mass alone. So we get 5 times 0.461 kilograms meters squared over 2 times 0.6 meters and then a squared. The meter squared here will cancel with the meter squared here, and that will give me 3.2 kilograms. And there we go. So quick note, list your givens, write your equation, plug and play, watch your units, and you basically can miss. As long as you do a good job of listing your givens, it does not matter what is missing. It's just a game of what do I have and what can I get with it. All right, for our last problem, let's up the level a little bit. And to do that, we are going to use this device. This is a piece of physics equipment known as a rotational motion apparatus or a spinning disc. That's all it is. It's kind of like a record, except if you look, it's pretty thick and obviously has a much more mass than a record. There's an axis here, and you could take the disc and just spin it. And since the axis is built to have as little friction as possible, it will spin around for a good period of time before it slows to a stop. So let's say you do that, and let's take a look at our problem. This rotational apparatus has a mass of 1.8 kilograms, a radius of 14 centimeters, and is currently rotating at 3 rotations per second clockwise. A student presses their finger against the side of the disc and exerts a 8 Newton perpendicular force to the disc edge, bringing the disc to a stop in 0.4 seconds. What is the coefficient of friction between the finger and the disc? So before we go anywhere, let's get a better point of view of what the situation is. And to do that, I'm going to draw an above view. And that would look like this. So one thing that separates this problem is this is definitely spinning clockwise. Now, unit circle, this would be a negative direction. But for the sake of simplicity, I'm simply going to make this positive. Because from a mental aspect, I think having the decrease in velocity shown as negative is going to make things a little easier to see. A side note, if you go against the norms for a direction like this, make sure you signify that to your grader or teacher. So we're going to make clockwise positive and counterclockwise negative. The finger presses on the disc with a force of 8 newtons. By Newton's third law, that means I have a force from the disc on the finger that is also 8 newtons. Now notice I have not labeled this, but if we think about it, this force is completely perpendicular to the surface, which makes this force normal. And the last part of this problem mentioned coefficient of friction. And if coefficient of friction is ever mentioned, you will immediately put down the force friction equation. Force friction is mu, or coefficient of friction, times force normal. And in this case, it's the coefficient of kinetic friction because it's sliding, but since static does not come into play, I'm just going to use mu from now on. Now, one thing I want you to have in your brain before I put it down is, what direction is force friction here? Well, since the disc is moving clockwise, force friction on the finger would be this direction. But we don't care about the finger. We are not tracking the finger. We are tracking the disc, which means force friction on the disc is this way, which makes sense because if the disc is moving clockwise, you would need a counterclockwise torque in order to slow the disc down. So one of the big things to notice is we have a bunch of third law pairs here. However, if we go way back to one of my really early videos, in any physics problem, you have to ask 3 questions. Number 1, what are you tracking? We are tracking the rotational device. We are tracking the disc. We are not tracking the finger. So we don't care about the forces on the finger. We care about the forces on the disc. 2, when does the problem start? Well, at the start of the problem, this is already moving at 3 rotations per second with the finger on it. 3, when is the problem over? The problem is over when the disc comes to a stop. So now that we have identified those 3 things and the proper direction of all forces, we can now start this problem. In other words, you can't do a physics problem if you don't know what the heck is going on. You need that conceptual understanding first. Now we can list givens. First, we're given mass as 1.8 kilogram. Radius is 14 centimeters, which I'm immediately going to convert to 0.14 meters because we do not use centimeters. We are given omega initial, 3 rotations per second. Again, I'm going to immediately convert this. Rotations to radians. When a rotation is 2 pi radians, rotations cancels. It's going to be 6 pi radians per second, or 18.85 radians per second. It says it comes to a stop, so omega final is 0 radians per second. We are handed a time of 0.4 seconds, and force normal is 8.0 newtons. So an important note here, a lot of people will see this force and confuse it for the torque force. However, to clarify, this yellow line is the radius. For a torque, I need a perpendicular force. This problem says the 8 newtons is perpendicular to the disc edge. It is also sometimes stated as the surface of the disc, which means it is this way, and that is not perpendicular to the radius. So you have to be very careful with the terminology here. Okay, all givens are converted. Let's see what we can find. I'm immediately seeing that we have enough to get acceleration here. Angular acceleration. Omega final minus omega initial over time. There is no omega final. So I have 0 minus 18.85 radians per second over 0.4 seconds. This is angular acceleration negative 47.13 radians per second squared. Again, I flipped the directions on purpose because I'm seeing this negative acceleration as the disk slowing down, which in my opinion makes things a little easier to understand conceptually. I'll put that here. It is a disk. I'm given the mass and the radius. Again, thickness does not matter. Moment of inertia is 1/2 mr squared, 1/2, 1.8 kilograms, 0.14 meters squared, 0.01764 kilograms meter squared. That's a new given. I am after a force, and this is a perpendicular force. And since it's a perpendicular force, this is screaming torque. Angular acceleration is net torque over moment of inertia. Therefore, net torque is moment of inertia times acceleration. 0.01764 kilograms meter squared times negative 47.12 radians per second squared gives me torque at negative 0.831 Newton meters. Now I have net torque. The force friction here is the perpendicular force. Torque is force perpendicular times radius. Therefore, force perpendicular is torque over radius, negative 0.831 Newton meters over radius of 0.14 meters. Meters is going to cancel, which is good. And at this point, I'm going to start ignoring the negative sign because I already have the direction stated in my diagram, which is much, much, much more valuable. Because again, when it comes to rotational, the direction of forces is much better done from a conceptual and visual point of view than mathematical. Because from the visual point of view, you can literally see what is going to happen. This is spinning clockwise. There's a counterclockwise torque, which means it is going to slow down. And force perpendicular is 5.94 newtons, which is really important to note that this is force friction. So force friction is 5.94 newtons. I'm going to borrow this space here in the lower right because we only have one more step to do. If this is my force friction equation, I'm going to rearrange it itself for mu. Mu is force friction over force normal, which is 5.94 newtons over 8 newtons. Newtons cancels, which gives me a coefficient of kinetic friction of 0.743. And coefficient of friction does not have a unit because, again, it is basically a percentage. Force friction is this percentage of force normal, or in this case, force friction, 5.94 newtons, is about 74% of force normal, which is 8 newtons. And this is the coefficient of friction between the finger and the disc. All right, so these three problems are really good ones to know, otherwise I would not have made them. And notice that our technique has not changed from the beginning of the year. Draw pictures, list givens, write equations, units, and in general, keep things nice and organized. All right, hopefully this helped you out. Have a good day. This is Mr. M, signing off.